Good morning, everyone, and welcome to MAE 209, Probability and Statistics. My name is Richard Kohar, and this is lecture 14. So we're going to cover a couple of distributions today. And the first thing I'm going to do, though, is cover just an example of the hypergeometric distribution that we did, the distribution that we did in our previous lecture. Just as a little reminder, we have a poll that's going on the Moodle webpage, so please cast your vote so that we know how to keep going during our transition period here at RMC. Okay. So here's our example. We have a purchaser of electrical components, and they buy them in lots of size 10. Oh, question about a hypergeometric versus binomial distribution. Is one with replacement and the other is not? Well, with the binomial distribution, it usually, with those three assumptions, that again, the trials are identical, so the probabilities are not changing. The second thing is that each trial has a success and failure outcome. And the third one is that each of those are independent. So I suppose you could say that it's like sampling with replacement then. Because again, if we think of this as, if I'm thinking about a deck of cards, for instance, and I say that I'm going to make a draw that's independent. Each draw is independent. Okay, I draw this card here, but if I put it back in, the probability that me drawing a 5 of, oops, I lost it. The 5 of spades doesn't affect it. So the fact that I drew a card on the first one, and if I put it back, it won't affect it. So if you have independence, then I guess you can think of it as sampling with replacement. But in the hypergeometric, there's sampling and it's not being replaced. So it does affect the probability. Okay. So yes, in the binomial distribution, there's independence, so you can think kind of that as a sampling with replacement. And so let's consider this example right here. We have a purchaser. They buy them in lots of 10. So this is important. 10. It's his policy to inspect 3 components from a lot and to accept the lot only if all 3 are non-defective. There's 30% of the lots have 4 defective components and 70% of the lots have 1 defective component. And then we're asked, what's the proportion of lots does the purchaser reject? So I'm just going to put away this pen, and I'll use, let's see, which one will I? So what I'll do is think of it with a tree diagram. So with this, we'll say think of it as a tree diagram. We'll say that this is lot A, over here is lot B. So we'll say A, and we'll say B here, and there's 30% of the lots are A, and 70% of the lots are B. And from there, we'll have two cases. So we can either accept or reject. And same thing over here, we can either accept or we can reject. Now, this is asking us what the proportion of lots does the purchaser reject. The first thing I'll do is I'm going to calculate this probability here, which is the probability that he inspects the three components and that he accepts the lot. So let's do that one. And then we're doing really an indirect method. So I have the purchaser accepts. So I have these two cases right here. I have for the first case here that it could be in lot A, so the probability that it was from lot A is 0.3. And then it's multiplied by the probability of accepting, given that we're in lot A, plus, now for this case we have that they're in lot B, and then we multiply by the probability that they accept, given that it's in lot B. So we're not quite done yet. We have to calculate that probability, this conditional probability here. So given that they're in lot A, so they will accept it if all three components that they pick are non-defective. So if we're in lot A, there's 4 defective components. So there's 4 defective components, and that means then that there should be 6 non-defective then. And he has to, well, we don't have a gender for this, so the purchaser has to accept it, so it has to, all 3 of them have to be non-defective, so he's going to pick none, or she. And same thing over here. So there's 4 choose 0. And here would be that they select the 3, and that's this is the defective. And over here, this is the non-defective. So they're choosing none of the defective, and over here, they're choosing all of the defective. And all the possibilities in the denominator. So we have 10 components, and they're selecting 3. So this is for the case where it's in lot A, plus the probability that they've selected from lot B. And over here in this case, again, it's still, there's 10 components, and they're selecting 3. But instead of having 4, there's just going to be 1. So there's 1 defective component, and then there would be 9 non-defective. So here's the defective, and here's the non-defective. So they're selecting 0. Over here is 3. And now as we enter that into the calculator, we get 0.3 times 4 choose 0, which should be 1, times 6 choose 3, divided by 10 choose 3, plus we have 0.7 times 9 choose 3 divided by 10 choose 3. Oops. Which gives us 5.4 for accepting it. So that means that the purchaser rejects it. Taking the complement of it. So again, that would be 46% of the lots are rejected. Okay. Here is another example or exercise. And this is an exercise from the textbook from section 3.5. This one says, a personnel director interviewing 11 senior engineers for 4 job openings has scheduled 6 interviews for the first day and 5 interviews for the second day. Assume that the candidates are interviewed in random order. What is the probability that X of the top 4 candidates are interviewed on the first day? So we'll say let X, and that will equal the number of top 4 candidates. Interviewed on the first day. So these are the successes. That's what we want. So in total, there's capital N. There's 11 candidates. Our M is, and of course, we're going to be modeling this using a hypergeometric distribution. So we're using our variables here. We have 4. That means that there would be 7 non-acceptable candidates. And lastly, maybe I'll switch to a different color. Some green. That, because again, we're interviewing on the first day, that there's 6 interviews scheduled for the first day. So we'll set N equal to 6. So those are kind of our trials, / our candidates. So substituting our values. So substitute those. For the hypergeometric, and what we get is Well, we're going to have 4 of the candidates, and we want to have the number of x of the top 4 candidates. So we'll say there's 4 top candidates, and we're choosing x of them, which means that I'm left with 7 of the candidates we don't want. So there's 6 being interviewed. Sorry, there's 6 in total on that day. So we'll have 6 minus x. And the total ways that we can do that, there's 11 candidates, and we have 6 interviews. And that is for x for the set of 0, 1, 2, 3, and 4. Then we have how many of the top 4 candidates should the personnel director expect will be interviewed on the first day? So we're still going to use our hypergeometric, and we're just basically asked what the expectation of x is. And using the formula for it, we get it's n times m over n. So the number of trials or the number of interviews multiplied by the ratio of candidates we want out of the total candidates. So there's 6 interviews multiplied by the total number, or the successful candidates we want, or the top 4 out of the 11. And so what I get is 6 times 4 divided by 11, which is approximately 2.18. So that's how many, so approximately 2.18 like top 4 candidates will be expected on the first day. Okay. Any questions so far? Okay. Then we can move on to the next distribution. So the next distribution that we'll cover is the negative binomial distribution. I should also mention that if you're in the class on Moodle, you can download the fill in the blanks version of these notes. So I've already kind of scanned them, posted them to the website, so you can download those. Oh, let me just switch back. There's a question, and that's how many candidates can be expected to be in the top 4. That's, yes, the top, about 2.18 top of 4 candidates will be expected on the first day. Yes, that's right, after interviewing on the first day. Okay. So we're going to consider an experiment that has the following conditions. The first one is that it's a success or a failure outcome for each trial. Number 2 is that each trial is independent. And this should start to feel familiar because, and lastly, okay, each trial is identical, meaning that each trial, the probability of success and failure is unchanging. So those are the three conditions that we have for the binomial distribution. So you can see why we called it the binomial distribution, is because we already are including the three conditions for it. So we have to have something a little bit extra to make sure that it's different. And that's where we have the fourth condition here. So in this case, the experiment is performed, or the trials continue until a total of R successes have been observed. So the negative binomial distribution will be, this is the random variable. So that's the negative binomial random variable. It's the number of failures that precede the rth success. So it could be the third success, the fourth success, and we want to know how many failures there were before that happened. If that's not too clear at the moment, well, we'll do a small example and motivate it so that we can get to the probability mass function that we're going to be using for this distribution. So the question then becomes, how is this different from a binomial random variable? And the answer to that is the negative binomial distribution has a fixed number of successes. So we say no, we say there's 6 successes or 7 successes. We fix that. And we let the number of trials be random. So in a binomial distribution, we have to fix the number of trials. And in a negative binomial distribution, we fix the number of successes. So if we think of this as we have B, and we had, say, X, we had NP. This is the binomial. Because we're fixing the number of n's and p, and we set the success probability. Well, in the negative binomial, we'll have the number of failures, and we'll set the number of successes and then the probability. So you can see here, we're setting the trials, and over here, we're setting the number of successes. So those are the parameters. So here's the example. Move that out of the way. So, consider a cadet who conducts a survey in the Mathematics and Computer Science Department hallway. The cadet approaches other cadets and asks if he or she would like to participate in the survey. In this case, a success would be if the cadet says yes, And a failure would be if the cadet says no. What is the probability that exactly 7 no's occur before the third yes? So in order for this to happen, well, there's exactly 7 no's and 3 yeses. So that means that we'll be looking at the 10th case, or the 10th cadet, the 10th trial. So there's kind of like we're looking at that. And there must be exactly 2 yeses among the first 9 cadets. So there's 2 yeses on the first 9 cadets, and then on the third yes would be on the 10th cadet. So just as we're looking at the first 9 trials, or the first 9 cadets. And then over here, this is the 10th cadet who says yes. So what is the probability that exactly 7 no's occur before the third yes? So what we're looking for here, well, we should define our random variable x. So we should say let x be the number of cadets who said no before the third yes. So in this case, there would be 7. In this case, now the other thing that we haven't done is we don't know what the probability of a cadet saying yes is going to be. So that is something that we need to add to this question. So what we can say is that let's say the probability the cadet says yes, and we'll use just P. So they're going to say, so what we know is we're going to have 2 yeses. We also know that on the third one, or the third yes, is going to be the 10th cadet, so we'll put this P right here. Okay, which means that the ones that say no, well, for the first 9 cadets, it'll be 9 minus 2, so that should be 7. And we also know that this could be, the order could be arranged differently. So we know that there could be 9 cadets, and we're going to pick 2 of them to say yes. And there it is. So there's our probability. 9 choose 2 multiplied by the 2 times, or where the cadets say yes, the 7 times where they say no, and then on the 10th case, they say yes. So we can simplify this by just collecting the p's here. So we have 9, choose 2, p cubed times 1 minus p 7. So what we can notice here is that here's our number of the successes. Those are fixed. So that's the 3. That's our parameter. And we also have the parameter of p of success. So it's just p. So just generalizing from this, what we have is our, well, we should let's define it. So we'll say let x be a negative binomial random variable. Or we can also say that x is the number of failures. Okay. So we can notice here that we have our variables. We'll have like little x is the number of failures. We'll have r is the number of successes. And that's fixed. So together, there would be x plus r many trials. And the other thing is p is the probability of success. Okay. So we'll have the probability of big X equals little x. So again, like we said, we have the probability of success, and that's going to happen r times. The probability of failures, there's 1 minus p, and that'll happen x times. And this is where it's a little tricky. So we see that 9, in this case up here, where we had the 10th cadet. So in total that there would be 10 trials, but notice that instead of 10 we have 9. So it's the total number of trials, so x plus r minus 1. And then we're going to choose one less of the success. And that's the PMF for the binomial negative distribution. Or sorry, the negative binomial distribution. And in the book, they keep using the negative binomial. They have the x and then the two parameters, which is r and p. And the expected value for that is r times 1 minus p over p, and also the variance. We'll state this without proof. Here we go, number 5. So here's an example. An engineering firm has 3 positions to fill, and they are interviewing candidates one at a time until all 3 positions are filled. The personnel director, based on previous data and experience, believes that approximately 10% of the candidates will possess the required skills. So we'll do the first part. What is the probability that the personnel director will interview exactly 10 candidates? So what we'll do is I'll say let x be the number of unqualified candidates before we have 3 qualified candidates interviewed. So in the chat, can you tell me what little x is equal to, what r is equal to, and what p is equal to? Yeah, that looks right. So okay, so I agree with the probability is 0.1, right? This is where we get it from. We get the is coming from the 10% right up here, right? I'm good with the 3 because that's what we're saying. That's qualified, and same thing here. There's only 3 positions. Well, there's 3 positions or 3 successful ones, right? But what is the x? Yes, the x that threw everyone for a little bit. Right? That's the number of failures. So in total, So in total, 7 plus 3 is equal to 10 candidates in total. So it's good to just be very careful about labeling it. So now we can proceed to just substitute the values into the formula. So the negative binomial distribution, we want 7. And r is equal to 3. The probability is 0.1. So we want it where it equals 7. So it's x plus r minus 1, choose r minus 1, multiplied by the probability of success to r, and then the complement, so the failure, to the x. So again, we get 9 choose 2, 0.1 to the 3, and 0.9 to the 7. So 9 choose 2 times 0.1 to the cubed times 0.9 to the 7 is approximately equal to 0.0172. And we'll leave part B as an exercise. Okay. Now we can move on to another distribution. This is called the Poisson distribution. And a Poisson distribution takes on values 1, 2, 3, all the way up to infinity. It's Poisson distributed with a parameter mu for some positive mu. This is the parameter. If it's equal to e to the minus mu times mu to the x all over x factorial. Now e is Euler's constant, so that's 2.718 ... or Euler's constant. So we have this very odd looking PMF. So first of all, let's show that it is a PMF. And the way that we're going to show that is we need to show that the sum of all the possible values sums to 1. So just a quick proof for that. So if we start to sum over from x equals 0, because we're starting at 0, going to infinity. So we'll replace this. So we have e to the minus mu, mu to the x all over x factorial. Well, the first thing I can do is I can pull out this e to the minus mu because it's not dependent on x. So that is just a constant. Now, this part right here should be somewhat familiar. This is the Maclaurin series for the exponential function. And in this case, it's e to the mu. So you can see that as the Maclaurin series. So I get e to the minus mu. I still have that there, and that's being multiplied. And I can use my exponent rules. Minus mu plus mu equals 0. And anything to the exponent 0 is 1. So in fact, it is a probability mass function. Good. So Poisson first introduced this probability distribution in 1837, and he was using it to investigate criminal matters at the time. He wanted to know about verdicts, lawsuits, and so forth, and so he was using this distribution that he came up with to analyze some of the data that he had. And it's actually quite useful in modeling many real-world applications. For instance, you could look at the number of misprints that occur on a page in a book, the number of people in Kingston who will survive to be the ripe old age of 100, number of incorrect telephone numbers dialed in a day, the number of alpha particles emitted in a fixed period of time from some radioactive material, the number of customers entering a bank on a given day. What it's really doing is it's trying to model things that kind of randomly happen through time. And so if you pick a certain day, you could think of how many accidents there could happen on a highway, number of wars in a given period. And each of those examples that I'm giving are approximately Poisson distributed for the same reason, all for the same reason here, namely that the Poisson distribution approximates the binomial distribution. And it does that, it's approximating the binomial distribution when n is large, so you have a large number of trials, and the probability of that event is very small. It's very rare. So again, in each of these things, the misprint is rare. The probability that someone will live to be 100 is quite rare. It's very rare somebody may incorrectly dial a phone number. It's rare that an alpha particle is emitted. Customers entering on a bank on a given day. Accidents, deaths, wars, those are very low event occurrences. So you could model them using a Poisson distribution. And to see this, that the Poisson distribution is an approximation of the binomial distribution, we'll just do a small derivation to show that. So what I'll say is we have to remember what our binomial distribution was. So here we go. So we have n choose x times the probability of success to the x, 1 minus p, so that's our failure, to the number of trials minus the number of successes. So what I'll do is I'm going to write this out more explicitly. So I have n factorial over n minus x factorial Now, what we're going to do, so to see that we're going to approximate the, using the Poisson to approximate the binomial, what we're going to do is we're going to let mu equal NP. So what that means is, we can just kind of rearrange that, P is equal to mu over N. So replacing P with this mu over N to the X, and similarly I have 1 minus mu over N to the N minus X. And I'm not quite done yet, so what I'm going to do now is that I can simplify this, right? I'm going to, with this part right here, basically I'm going to cancel it out. So I'm going to have, I'll have N times N minus 1, dot, 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 all the way down to N minus X plus 1, all over. So that's that part right there. Which is the next part. So I can write this as, maybe I'll do it as an extra step. So I'll leave that, but I still have this x factorial. So I'll write that down here. X factorial. I'm going to write mu to the x over n to the x. And I can actually write n minus x as using my exponential rules, my exponent rules, that I can have 1 minus mu over n, and that's n. And down in the denominator, I can have 1 minus mu over n and x. So that's by my exponential rules. And I'm going to just kind of rewrite, just kind of bring this one and this one here together. All right, mu x over x factorial So again, by our assumption, if we let n get really big and p go really small, so as n gets really big, and mu is moderate, well, what ends up happening is that 1 minus mu over n is approximately equal to mu to the, e to the mu. This part right here is approximately equal to 1. And lastly, the bottom part right here is approximately 1 as well. So what you end up happening here is that you have, this is 1, this is e to the mu, this goes to 1, so this goes to 1, I'm left with this, and over on this side I'm just left with e to the minus mu. So what that means is all I'm left with is 1 times mu x over x factorial, and I'm left with this blue part, and that is just e to the minus mu. Which is what we wanted. Again, that matches the formula that we had introduced at the beginning. Perfect. So, in summary, the binomial distribution is approximating the Poisson distribution. As n gets really big, p gets really small, and that n times p is converging to mu. So what would be really nice is that what you'll see is it makes it very easy to remember what the expected value is of the Poisson distribution. So if it's NP is converging to it, well, that means that NP is mu, and 1 minus p, well, p is going to 0, it's getting really small, so that's just 1. So that just means that it's mu. So it makes it easy for us to remember that with the Poisson distribution, that the expected value and the variance is mu. Just give me a second to number these. So thinking back to our examples, we can see why it's Poisson distribution. For the number of misprints that occur on a page in a book, we can see that the probability of p is very small, of each letter being typed on the page being misprinted. So we can think of those number of misprints on a page can be approximated by a Poisson distribution, where we set the parameter of the distribution as equal to NP, where n is the number of letters, NP is this very small probability that the letter will be mistyped. And the same thing that happens, like I said, about the number of people in Kingston who will survive to be 100 years old. The probability of that happening for a person is very small, and you can approximate the number of people in Kingston by multiplying the number of people in Kingston by that probability. And that would be the parameter for the Poisson distribution. Okay, let's take a break for 10 minutes, and we'll resume more about the Poisson distribution after that. Okay, so is everyone ready? We can start to resume our discussion about the Poisson distribution. Okay. So let's do an example. Suppose that the number of typos on a single page of a textbook has a Poisson distribution with parameter 1/4. So that's all we need. We just need that mu or our parameter for this distribution. Calculate the probability that there is at least one error on that single page. So we should say let x be the number of errors or number of typos on that single page. And so it's e to the minus 1/4 multiplied by one quarter to the x all over x factorial. And that would hold for all the values x 0, 1, 2, 3. Now, this could be quite tedious if we say that we need to calculate the probability of 1 error, the probability of 2 errors, the probability of 3 errors. So instead, what we'll do is we'll calculate the probability of at least one error by calculating the probability of none. So we'll do 1 minus no errors. Now substituting our values into it, we get e to the minus 1/4 times 1/4 to the 0 and 0 factorial. So that just is 1. So you can have 1 minus e to the minus 1/4. And that is approximately equal to, so on a calculator like this, 1 minus, and we have e to the minus 1/4, and that's approximately equal to 0.221. Oh, sorry, no, that's the probability. Of one or more errors on the page. Okay, so Here's another question. This says, suppose that the probability of a battery produced by a certain company will be defective is 0.1. Find the probability that a sample of 10 items will contain at most one defective item. So we can use the binomial distribution to do this. And the other one that we're going to do is we'll compare our approximation from the Poisson distribution. So I might just grab a little bit more paper. Okay, so with this, with the binomial distribution, we can let n equal the number of trials, so that's 10, and the probability of success is 0.1. Again, success is in those air quotes, because this is for the success of finding a defective battery. So if we let x be a binomial RV, then what we want is the probability that will contain at most one defective. So the probability that x is less than or equal to 1. So that means the probability of x equals 0 plus the probability that x equals 1. So there's 10 trials, and we want 0 of those, the probability of success, and we want 0 of that times the probability of the complement, and that's going to happen 10 times. Okay, and does somebody want to punch that in to see what the answer is? What answer do you get? Any answers yet? .736. Yeah, I think that's right. 10 choose 0 is 1. 0.1 to the 0 is still 1, so you're left with 0.9 to the 10. Plus 10 choose 1 is 10 times 0.1 times 0.9 to the 9th. And so I can quickly check 0.9 to the 10 plus 10 times 0.1 times 0.9. Perfect. So the next thing that we want to do is compare that to the Poisson distribution. So in this case, we have the Poisson. And we only have one parameter in this case, so it's going to be mu is equal to NP. Or we could do, so it's 10 times 0.1. So that should be just 1. Okay. We'll let y be a Poisson random variable. And what we can do then is, that's again the probability that it equals 0 plus the probability that it equals 1. So in this case, it's e to the minus 1 times 1 to the 0 over 0 factorial. So it's still, that's 1 plus, over here I'll have e to the minus 1. Then I'll have 1 to the 1 over 1. So again, that's still 1. So I get e to the minus 1 plus e to the minus 1. So you get 0.367. I'm going to multiply that by 2. And so that approximation is 0.73. Well, 5, okay, we'll round up to 6. And isn't that interesting? It's very close. Well, actually, in this case, the approximation is equal to it. So again, we can use the Poisson distribution for when we have a large number of trials and a very small probability of P. So again, things like accidents, earthquakes, sometimes deaths. But again, it comes down to the fact that it's very useful that the expected value of the Poisson distribution is the same as its variance. Okay, so I'll do a small proof of the expected value. So we'll start off with the expected value. Here we go. And we start off with the definition. It's always good to review, but it's the summation of all the x's of the value times the probability of it occurring. Now, the values that x can take on is from 0 to infinity. So I can have x times, and then I'm going to put in the PMF. So it's e to the minus mu, mu to the x, all over x factorial. Now, what I'm going to do is I can increase my counter up to x equals 1, because for x equals 0, the term is 0, okay? Because of that x. So what I'm going to do is I'm going to start now at 1. Now what I can do is I can see that here what I have is x over x factorial, or I could see that as x times x minus 1 factorial, and so that cancels, and so I'm left with 1 over x minus 1 factorial. So that's what's going to simplify here. I have e to the mu, and I also have, I'm going to write as mu times mu to the x minus 1 So that's all I've done here. From here, I've just split that off. And now, what I can do is I see this part right here, the e to the minus mu times mu, that doesn't depend on x. So I can bring that out in front. So I have e to the minus mu, and I have this summation of mu x to the minus 1 over x minus 1 factorial. I'm going to change my, let's call it my counter variable. So let's let y equal x minus 1. And so what I'll have is y equals 0 to infinity. Have mu to the y over y factorial. And as I said before, this is equal to e to the mu, because that is the Maclaurin series. And it's from our first year calculus course. Oh, I can't use that same variable. I have to use something like I or something. So we're almost done. By my exponent rules, I can combine those because they're multiplication. So mu minus mu plus mu e to the 0, which is 1. And I'm still left with the mu, and that's it. So there's the proof of the expected value. So we did an infinite sum of each of the PMF. So we did it, and there it is right there. Now, there's another thing that we can do, and we're going to talk about the Poisson process, and it's known as a type of counting process. So another use of it is in situations where events occur at random times in a time interval. Okay? And under certain conditions, those conditions, again, they're in the textbook. Under certain conditions, these events in a specified time interval can be counted. So the number of events occurring in any interval of length t is a Poisson random variable with a parameter they will call alpha t. Now alpha would be then the rate. So to be precise, let us call the interval from 0 to t and denote the number of events or the count occurring in that interval by nt. So then the probability of the number of events k, so we'll say that it happens k times in that interval is, and this is where I have to write it in, but all I'm doing is just replacing this parameter alpha t in the Poisson distribution. So it's e to the, not mu, minus mu, but it'll be alpha t times, not mu, but it's going to be the parameter alpha t. We're going to do it k times all over k factorial. So k is the rate of the process. Now in the textbook they kind of give it a different notation, but I think this makes more sense. They use p sub k t, but what this says is this is the probability of the number of occurrences in t, and it's going to happen k times. So examples of this type of counting process, or this Poisson process, is the number of earthquakes to strike a city during some fixed time span. Again, earthquakes are fairly rare, so should follow. The number of wars per year. The number of electrons emitted from a heated cathode during some fixed time interval. The number of deaths in a year of policyholders of some particular life insurance company. So we can do an example here with an earthquake. So suppose that earthquakes in the eastern part of Canada follow a Poisson process with alpha equals 2 in 1 week. So to be a little bit more specific, that means that the earthquakes occur at a rate of 2 per week. We're asked to find the probability that at least 3 earthquakes occur during the next 2 weeks. So we need to translate, I should try to keep that up on there as well. But we need to translate this into symbols, mathematical notation. So it's the probability that the number of earthquakes in the next 2 weeks, so we're going to be on a time scale of 2 weeks, is greater than or equal to 3. So the way that we could do this is 1 minus the probability of n2 less than 3, which means that we need it equals 0 plus, I need to consider the case where it's equal to 1. Oops, and not 2. Okay. And when we look at that, our alpha t, so that's 2 times 2, which means that it's 4. And we just substitute into the values in here. So I need to calculate it for when it's equal to 0. So it's e to the minus 4, 4 to the 0 over 0 factorial plus e to the minus 4, 4 to the 1 over 1 factorial plus e to the minus 4, 4 squared over 2 factorial. And we can sum those up. So this is 1, this is 1, this is 4, 16 over 4. So that should be 13. And if you'd like an approximation, we can pull out the calculator here. So we have 1 minus 13, which gives me approximately 0.762. So that's the probability that at least 3 earthquakes will occur, at least three earthquakes or more will occur during the next 2 weeks. lining that up just a little bit. The next part of the question is find the probability distribution of the time starting now until the next earthquake. So what we'll do, so let X denote the amount of time in weeks until the next earthquake. Because X will be greater than t if and only if no events occur within the next t units of time, we have from that equation that the probability of X being greater than t so this is the probability of n of t equals 0. So if we set that equal to 0, that means that k is equal to 0. So we put in 0 here and 0 there. And so this term goes away, and we're just left with e to the minus alpha t. So e to the minus alpha t. And so the probability distribution maybe the cumulative distribution function, we'll say f of the random variable x is given by so we have f of t is equal to the probability, and again it's going to be x is less than or equal to some point of time t. And then again, we can take the complement of that, so the probability that x is greater than t, but we've already calculated what that should be. And we've already calculated what alpha, well, we know what our lambda, or well, our alpha was, because we said that our alpha was 2. So we can just substitute that in. Okay, so is there any questions about, we covered a lot of material today. We covered some examples of the hypergeometric distribution. We did the negative binomial distribution, and we did the Poisson distribution, and we also even covered the Poisson process, which is counting rare events. So is there any questions before we sign off for today? If you have any questions, feel free to send me an email, again, through my RMC account. And feel free, we can always set up office hours through Zoom. Just as a general reminder that there is a poll asking about your preferences for for how you'd like to continue the course, either through online delivery or in person. So that feedback is very helpful for me. Okay, thank you. Have a great day. Is the quiz starting from the midterm? Yes, so that will cover material that we did on Tuesday and today, and also on next Tuesday's lecture. Questions for the chapter 3 is posted, so have a look at those. Okay. Well, take care, everyone, and if you have any questions, again, I'm just an email away. Okay. Take care, everyone.